Uh, are you guys ready? Looks like it.
Yes, it's all you
Okay.
now.
All right. All right. Swell. Uh, okay. So let me just start by saying, Venus, volcanism is at the heart of considering Venus as a system that connects the interior, the surface, and the atmosphere. Of course, the upper mantle provides the heat and the material for volcanism that reshapes the surface, and eruptions deposit volatiles into the atmosphere, and all of these things interplay with each other and provide controls on how volcanism behaves. So what I'm going to do is kind of provide a survey of volcanism on Venus and highlight some of the ways that the different approaches that have been used to take the volcanic record to try and understand both the surface history and aspects of the surface, aspects of the mantle and the atmosphere. So as I go through these, you'll see that most of the slides involve pulling figures from a bunch of the work that's been done over the years, and I'll have put the reference at the bottom of the slide so that if some of the younger scientists in the room want to go back and think about some of these topics, there'll at least be one starting point that they can use to explore some of this. So next slide, please. And so you guys are changing the slides. There we go. All right. Great. All right. So let me just start by, as the data was coming back from Magellan, there was a group that was headed up by, largely headed up by Jane O'Bell and Larry Crumpler, who graciously hosted our last VEXAG meeting. And that group undertook sort of the Herculean task of cataloging and characterizing all of the volcanic features on the surface. And I just want to point out a couple of things. By necessity, the way they were cataloging things involved using just the imagery. And so they were characterizing things mostly by the area that the flows that they could observe from individual volcanic features covered. And so that's a little bit different than the way things are done typically on Earth, where you're able to kind of figure out the whole volume of a volcano and learn things about its elevation and stuff like that. So kind of bear that in mind when you're using this volcano, or using this catalog, that they had this limitation. For instance, one of the things that means is that some of the volcanic features that have been partially buried by other volcanic features will show up as smaller in the catalog than they probably were when they formed, and things like that. So and then of course, this was done way back in the early to mid 1990s, and my understanding is that there's a new catalog that being developed by Hahn and Byrne that we're going to hear a little bit more about today. So keep that in mind. All right. Next slide, please. All right, so with that, let's just start going through some of these features and talking a little bit about them. First, let me just start with the largest volcanoes on Venus. Some of these things cover an area that's over 1,000 kilometers across, so that's really quite large by, say, terrestrial standards. You're talking about something that would cover say the entire state of Arizona or Montana. And the thing that I want to highlight here, of course, there are some really large shield volcanoes, and then there are these similar size features that Dan talked a little bit about in the last talk, corona that are sort of flatter with a raised rim. And then there's a spectrum really of features that span from what you would call a typical shield volcano to a typical corona. And there's, I think it's an interesting area of study to try and figure out why you get a corona and why you get or why you get a large shield volcano, and that plays into the behavior of the upper mantle and the lithosphere. And there's been a couple of ideas floated for why that is, related to perhaps the duration of the plume and its effect on the volcanic product, and also the state of the lithosphere and how thick and strong it is when you're in placing a feature. So, all right, next slide, please. So if you look at the pattern of, and Dan talked a little bit about this last time, if you look at the pattern of the largest volcanoes and the coronae and the rift system, and you compare that to the geoid, which you can sort of use as maybe a proxy for mantle convection, what you see is that where you have large geoid highs, that tends to be places where the rift system has intersections and you get large volcanoes on there. And then the coronae tend to be along the rifts, but avoid large geoid, the large geoid highs and the large geoid lows. And so this is telling you something about how the interior is behaving in relation to the volcanoes and the coronae, and similar, both myself and Catherine Johnson and Mark Richards had some ideas about how that reflects today's geodynamic regime. All right, let's go on to the next slide, please. Okay, so moving down in size, there's actually, so there's a variety of different types of volcanoes that occur in what the Crumpler et al. Catalog has as sort of mid-sized volcanoes, which really are also still pretty large by terrestrial standards. They're sort of in the 50 to 200, covering an area maybe 50 to a couple hundred kilometers across. Interestingly, to go back to the previous slide, the intermediate size volcanoes also, like the coronae, seem to avoid both the geoid lows and the geoid highs. And so I think that means something, not sure exactly what. And then going down to smaller size volcanoes, of course, you can see, as shown in the upper left of this slide, you can see that there are volcanic features that are going down to the limit of Magellan resolution. And a lot of these small shield volcanoes occur in clusters. And the smaller, these small shield fields are thought to have a significant role in placing the low-lying volcanic plains. And then you also see some of these shield fields up in some cases near the summit of some of the larger volcanoes. So let's see here. All right, next slide, please. Okay, so another thing of interest, if we can find them, are volcanic features that are produced by silica-rich lavas. That would be telling us something unusual about the lithospheric and source material for the volcanoes. It's in general terms, if you don't have a lot of volatiles, you tend to end up with basaltic lavas. So finding silica-rich features is of interest on Venus. There's a couple of things that have been floated as possible uh, uh, features that are from silica-rich lavas, namely the festoon flows and the steep-sided domes, which have also been called the pancake domes. And the basis for thinking these are produced by silica-rich lavas is the resemblance to terrestrial features, at least in some ways in terms of the morphology. However, there's been some work that has, I would say, cast pretty credible doubt on that interpretation. The pancake domes, I think, in terms of their surface roughness, they're really quite smooth on the tops, and so that and they're also much larger than the silicic domes that you see on Earth. But the festoon flows, it's mainly there's been some work by Alan Treeman and one of his students he's worked with, suggesting that the margins of the festoon flows are not quite right in terms of their morphology for these to be silicic lavas. So I think we'll be able to resolve this issue with the data that will come back from the upcoming missions. All right, next slide, please. All right, so another source or another type of volcanic feature that perhaps is indicative of a volcano that erupts with unusually high volatile content is identifying pyroclastic flows on the surface. And there are just a few places where I think a pretty credible case has been made that you can see pyroclastic flows on the surface of Venus. But I think the interesting thing here is that, and I don't think a lot of detailed thought about this has been done so far, is why are there only a few places where you see what you would think is pyroclastic flows? Does it mean that these are really unusual places where there's some pocket of water-rich material in the near surface, or is it that maybe there are more locations of more past eruptions of pyroclastic flows, but the pyroclastic flows are so ephemeral that they get rapidly weathered away or blown away or covered, and only a few places are they well preserved. So not much has been done so far, I would say, in the grand scheme of things with these pyroclastic flows. Interesting features, though. All right, next slide. All right, so getting into some of the even more unusual volcanic features on Venus, the canali here. So there are some lava channels on the surface of Venus that extend for, over, some of them are a few thousand kilometers long, and so um, these are useful in a couple of ways. First of all, they may or may not be indicative of requiring some really exotic lava in order to make a channel and be able to travel across the surface such long distances without solidifying. So once again, perhaps an unusual uh, uh, crust upper lithosphere source region. But then the other thing that they've been done, because presumably they were placed over a fairly short period of time, they've been used as a stratigraphic marker, a time stratigraphic marker for a large chunk of the planet. So, and so from that, they've played a significant role in trying to understand the overall volcanic and tectonic history of the planet. Next slide, please. All right, so this is an image of Mylita fluctus, which is a pretty good analog for some of the flood basalts that occur on Earth. And in what way is it an analog? Well, it's so we have what appears to be flows that flow over you know, 1,000 kilometers or more over pretty flat terrain, and all coming from a single or very limited number of source regions. So I think the interesting thing is to try and think about the role of things like this versus the small shields in terms of forming these vast areas of volcanic plains. There aren't a whole lot of these sort of fluctus features that have been identified on the surface, but is that because they're not that common in forming the plains, or is it that Mylita fluctus is unusual in the sense that the individual flows are vary so much in terms of their the backness, in terms of the backscatter properties. Sorry. And so in terms of the big picture of how the plains are formed, I think there's a lot of area, the low-lying plains on Venus, where it's pretty tough to figure out whether they were produced by sort of large flood basalt-like events or lots and lots of distributed small sources that we just can't see. And so the higher resolution imaging that's going to come up is, I think, going to be important in terms of separating those two ideas out. All right, next slide, please. All right, so finally, let me just briefly mention that there's this area that of these features which Dan talked a lot about in the last talk. But you know, of course, if large chunks of the tessera are produced or were produced by some sort of silicic volcanism, that has huge implications for the history of the interior and the atmosphere and the overall climate of Venus in the past. And I just wanted to briefly mention that the role of these sort of inner tessera plains is in the grand scheme of things is also something that a few people are thinking about and have some important implications, whether these are sort of areas of plains that were left undeformed in the process of forming the plane, forming the tessera, or whether there's some later episode of volcanism in the tessera after it's formed. I think we're gonna, this is a story that's still being unraveled. All right, next slide, please. All right, and you actually seen the graph on the right here, and I'm going to mention it again in terms of there's been a group, Misha Ivanov and Sasha Basilevsky and Jim Head and some of their colleagues have sort of looked at tried to use geologic mapping to understand the sequence of events, and they have come to the conclusion that there's been an evolution in that this distribution of features that I've shown you in terms of volcanic features they were not all in place in different places everywhere, but instead there was an evolution in the nature of volcanic features that have formed over time, and that at the current time were dominated by just the large volcanoes, and that's where so a very limited portion of the planet is currently active, and those are mostly the areas where you have the big volcanoes. All right, next slide. And as I'm sure you're aware, there is a competing view to this, where that it has been argued that there are lots of different evolutionary scenarios. There's more inherent ambiguity in photogeologic mapping than is commonly understood, and that in fact there is less directionality than has been interpreted previously in terms of how these volcanic features have been in place. All right, next slide, please. All right, just as an aside, I think in terms of understanding this history, understanding the interaction of volcanism and the impact craters is important. As it currently stands now, I think I've made a pretty good case over the years that the craters with radar dark flows have in fact experienced some volcanic filling, but you can still reconcile that with kind of the directional view of that Ivanov and colleagues have put forth. If you simply say that whatever volcanic filling you see in these dark floored craters, it's really sort of the last dying gasp of a volcanically dying planet. All right, next slide, please. So finally, I want to mention that if you in any of these world views of how volcanism interacts with the interior and the atmosphere to create a history for the planet, an important boundary condition is understanding what the current and recent levels of volcanic activity are on the planet. And so in terms of recent activity, there's been both infrared and microwave emissivity have been used to argue that there are very young lavas on top of some of the large volcanoes, and potentially in some of the rift systems as well. Next slide, please. And recently in the literature, there's been a rather lively debate about what you might expect in terms of present day volcanic activity on Venus if you appropriately try and take Earth's current level of volcanic activity and transport it to Venus, and how would you do that, and what would the constraints be, and what does that predict on terms of how many eruptions you should see during the upcoming missions, and between Magellan and Arecibo data and the data that will be collected by Veritas and Envision. So I think it's reasonable to say that we will definitely see some eruptions with the new during the upcoming missions, and so there's going to be stuff to see. All right, next slide, please. All right, and finally, as part of this, of course, volcanism deposits material into the atmosphere, and so the record of observing sulfur dioxide in the atmosphere over time, there's pretty compelling case that some level of volcanism needs to be taking place in order to make the clouds yellow on Venus. And I think an exciting part of this is that potentially with the upcoming missions, we will be able to use spectroscopy and occultations in order to see an active eruption and then study its effect on the Venusian atmosphere. So, all right, next slide, please. So let me just put up the summary, and we can kind of start the discussion. But basically, Venus has really, I think, just an amazing variety of volcanic landforms. Some of them are pretty exotic by terrestrial standards. The spatial distribution of them, particularly in relation to proxies for mantle convection, tells us a lot about what's going on to the atmosphere, what's going on in the interior. The timing and composition of the eruptions informs our understanding of the history of both the interior and the climate. And this all feeds into our big picture views of how Venus behaves as a system. So I'll stop there. Thanks.